All right, let's get started. So we're talking about partitions, and today we're going to talk more about partitions. And I want to remind you of the last thing that we proved last time, because of the number of partitions of n into odd parts is equal to the number of partitions of n into distinct parts. So we proved this last time. I wanted to start today by showing you a similar identity. And actually, let me remind you that we gave a couple of proofs of this identity. One was using power series, and the other one was giving a bijection where base 2 played a very important role. And Krista asked me, why base 2? Why not use another base? And we talked a little bit about how the fact that we were talking about odd parts made the base 2 important, and I don't know, the proof works out for base 2 and for odd parts, but I actually wanted to show you a similar result where it's not the number 2 but the number 5 that plays a very important role. So here's another proposition that's kind of similar to this one. This is that the number of partitions of n into parts which are either congruent to 1 or 4 mod 5 equals the number of partitions of n whose parts differ by at least 2. So you're not allowed to use k and k plus 1 as parts.
Do they also have to be distinct?
Yes, because if you had 2 equal parts, they would differ by 0. So yes, you can think of this as number of partitions of n into parts which differ by at least 1, and here they differ by at least 2. And so here this is equal to the partitions of n into odd parts, and here they are the partitions into parts which are 1 or 4 mod 5. And there's another one, which maybe I won't write down, but I'll just say it out loud, which is the following. The number of partitions of n into parts which are either 2 or 3 mod 5 equals the number of partitions of this kind where you're not allowed to use the number 1 as a part. So this is so these are kind of, in some sense, mod 5 analogs of this statement. And let me restate this also in the language of generating functions. There's a generating function restatement of this, which is this, the product over k congruent to 1 or 4 mod 5 of 1 over 1 minus x to the k. So this is the generating function for the left-hand side. This is equal to the sum over n greater than or equal to 0 of x to the n squared over 1 minus x squared up to 1 minus x to the n. So it should be clear to you guys that this is the same as this. This is the generating function for this. It's less clear why the right-hand side is the generating function for the right-hand side here. But it is. Maybe that's like a nice exercise for the forum. This is, and let me also mention that if you change for 2 and 3 here, instead of 1 and 4, then you get the same thing, but with x to the n squared plus n. And then the denominator is the same. Okay. So we were just talking offline about how some of us in this room are kind of OCD. Can't seem to be happy with where I put that to. Okay. Now I'm okay. Now I can keep teaching. Okay, so combinatorial statement is in some sense an analytic statement. And these two identities that I just mentioned are known as Rogers-Ramanujan identities. You might know the story of Ramanujan, who was doing some of the most revolutionary mathematics in history on his own in India. He has an immense amount of identities, many of which have to do with partitions and things like this, and this is a good example of one of them. I wanted to show you this because it's a nice identity, and a nice theorem, but also because this is a lot harder than that, and I think that's kind of interesting. You might think that since that took us one board and a short discussion, maybe this should take us not much more than that. But it turns out this is a lot harder. For example, the analytic proof of that was fairly simple. I mean, it has some cleverness, but it was fairly simple. Whereas all the analytic proofs of this are pretty involved. They're very intricate. And where we gave a bijective proof here, it was an open problem for decades. I think Ramanujan died in the 20s, and it was only in the 80s that the first combinatorial proof of this fact was discovered. And it's a very hard combinatorial proof, and somehow it's not as nice as we would hope. And somehow some people still have the hope that we could find a nicer proof that really gives up a very explicit bijection. The proof is not so explicit. It's a bijection, but it's very complicated.
In those 60 or so years, was there another proof that wasn't a combinatorial proof? Or was that the first proof of that problem?
So there were analytic proofs before there was a combinatorial proof. But it is also true that Ramanujan somehow was discovering these incredible identities, some of which he had proofs for, some of which he kind of wrote and said this is true, and they weren't necessarily proofs written down. And still to this day, there's a lot of mathematicians, very good mathematicians, that are kind of making a career of understanding what he had in mind when he was writing these identities, or proving some of them that have never been proved, etc. Yeah?
Is it actually useful, or is it just kind of cool that they're equal?
Is it useful? I'm not sure, but it's beautiful.
Yeah.
Right? I don't know that there's like an application of this in cryptography or anything, but it's a very beautiful fact. So yeah, anyway, that's a nice thing that I thought you should know about and that you can investigate further if you're interested in it. Okay. So now I wanted to show a similar result, or a related result, which is that, let me add a third equality to this. This is equal to the number of self-conjugate partitions of n. So remember that every partition had a diagram, right? Where if you had the partition 531, then you would put 5 boxes, then 3 boxes, then 1 box. And remember that conjugating the partition was just flipping the diagram across the diagram. And so here what we're doing is counting the partitions such that they are their own conjugate. And the fact is that the number of those is also equal to the number of partitions into odd parts. That's kind of a cute result. And so let's give a simple proof. So maybe I'll draw. I think today, a lot of the class, you're going to have to just watch me draw lots of pictures. I hope I'm not too slow. I'm just drawing some self-conjugate partition here. That's the idea anyway. So if I should put the same length here and here, yes. And then maybe I can put a part here. If I do this, then I also have to do this. Maybe we'll go like this. Okay. So that's a self-conjugate partition. 1, 2, 3, 4, 5, 6. 6, 5, 3, 3, 2. Okay. So it's a partition of, I don't know, whatever the sum of those numbers is. And now I need to somehow find a partition either of this type or of this type that corresponds to it. And it turns out that there's a fairly simple way to do this. Just to now look at this here. Okay, so how many boxes do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let's make a part of length 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Then, how many are there here? 9, right? So, we'll go make a part equal to 9. And then, look at this, and I have 5 boxes, and so I make a part of length 5. Okay. So this gives me the partition 11. 9. Okay. A partition into odd parts. So that's the bijection. So like I said, it takes longer to draw these pictures than to actually explain them. And I mean, why are they odd? Because each one of these hooks is of odd length, because this is symmetric across this diagonal. And you know what? Actually, this is not true. Can you see why this is not true? So it is true that starting from here, I get a partition into odd parts. And what's the inverse? Well, the inverse is just kind of, go like this and just break each piece in half, right? Can I always do this? Well, there's one issue, which is that imagine that this part was also equal to 11, the red part. If that red part was equal to 11, then I would have an extra box here and an extra box here. And that would not be a partition. And so, you see what I got here is a partition into odd parts which are also distinct. Okay? So clearly I made a mistake when I was preparing class. It's not this, it's into distinct odd parts. Okay. Just from the construction you can see that each part is smaller than the previous one. And it's also clear how if you take one of these things and you just bend it in half at the middle, you can get a self-conjugate partition. And So this is, sometimes people will actually, there's a book that's called Proofs Without Words, and this will be an example. Something where trying to explain it would look more complicated than actually just showing you a picture that's pretty eloquent, I think. Do you have a question?
Sorry, why if you had two 11s it would not be a partition?
So if I try to put two more boxes here and try to build an inverse to this map, then I would say, okay, well, first take the 11, break it in half, or bend it in half and put it here. Then take the next 11, bend it in half and put it here, but you see it's going to stick out. And it can't stick out because this is supposed to be a partition, meaning that the parts should get smaller as you go down. That's the key point that I didn't say. That in a partition, the parts need to be decreasing, so you can't have a one and the next one be longer than it. So that's why. Cool. I was thinking as I was walking here that I didn't know that these three things were equal to each other, and they're not. Okay, so there's two different statements here. One, that the number of partitions into odd parts equals the number of partitions into distinct parts, and also that if you have distinct odd parts, then you get the same as self-conjugated partitions. All right. Cool. So now let's look at an identity that is pretty close to this one actually, but easier. Proposition. Product of 1 over 1 minus tx to the I greater than or equal to 1 probably, yeah, equals sum over n greater than or equal to 0 of t to the n, x to the n, over 1 minus x, 1 minus x squared, to 1 minus x to the n. Okay. Okay. Well, if you had just walked into this class today without being here for the last few weeks, you might say, well, this is not a combinatorics identity. This is just some equality analysis. But given what we've done, we recognize that this has to do with partitions. Right? And so let's figure out what this means and why these two sides are equal to each other. Okay. What we're going to do is basically give a bijective proof. So let's figure out what this is. So what is the left-hand side? Well, we know that, let's do first 1 minus tx. So that's 1 plus tx plus t squared x to the 1 plus 1. Being a little bit deliberate in how I write this. You'll see why in a second. So then, next one, 1 over 1 minus tx squared is 1 plus tx squared plus t squared x to the 4th, which I write as 2 plus 2, etc. Then 1 plus tx cubed plus t squared x, this, etc. So on. Okay. So what is this? Well, we actually did this already without the t, right? And so we said that this was actually a sum over partition of lambda partition, and I mean the point is that whenever we look at x to the n, the ways of getting x to the n, I'm repeating what I said already, is just you need to make an n out of adding some 1s, adding some 2s, adding some 3s, etc. Okay. And so if you forget the t, actually, maybe let me color code this so that we can keep track of each part of this independent. So because again, remember that if I don't know, if lambda is the partition 4, 3, 3, 1, 1, 1, then it contributes one term here, which is x to the 1 plus 1 plus 1 times x to the 3 plus 3 times x to the 4th. This partition contributes this term if we ignore the t's, if we set t equal to 1. Okay? And so what we get in the end is x to the, I'm not sure if I mentioned that this is the sum of the numbers in the partition. Okay, in this case, lambda is maybe 4 plus 6, 10, 13. Okay? So each partition contributes this, but it also contributes t to the something. And so our next job will be to figure out what is that power of t. So what is the t in this case? Well, we can see that here, this guy has a t cubed in front, this guy has a t squared in front, and this guy has a t to the 1 in front. And the exponent of t, you see, is actually just the number of parts that you have. So here I have a 3 because I have 3 1s, here I have a 2 because I have 2 3s, here I have a 1 because I have 1 4. And in general, I get t to the 3 plus 2 plus 1 because that's the length of this partition. So t is going to be raised to the length of that partition. Okay. In this case, the length of the partition is 6. Okay? And so you see the left-hand side is actually just counting partitions. And it counts them according to what they add up to and how long they are. So the coefficient of t to the a x to the b is the partitions of b having length a. Okay? And so that's why this is having to do with partitions, and somehow we have to now figure out why that's equal to this. Okay? And so maybe I'll erase this stuff here. Because you see what the right-hand side is doing is that it is expanding this according to their power of t. And again, maybe that'll be a little bit clearer if I color code this a little bit. So this t is red, and this t to the end is kind of, you can imagine that it's out here. I put it out there so that you imagine that I'm doing the sum over n greater than or equal to 0 of the coefficient of t to the n is this thing. So what I have to justify is why this is the coefficient of t to the n here. So, well, I know what the coefficient of t to the n is. It's looking at partitions of length n. So the coefficient of t to the n in the left-hand side is this, the sum over the lambdas having length equal to n of x to the lambda. Okay, that's how I can get a t to the n here. Now, you'll remember that actually we already computed the generating function for partitions having length at most n. So maybe I'll remind you that, well, maybe I'll remind you exactly what that looked like in a second, but let me just say that this is the same thing as the sum of partitions of length at most n minus the sum over partitions of length at most n minus 1. Right? If you look at the things that are at most n and you subtract the things that are at most n minus 1, then you're left with the ones that have length exactly n. Okay? But the thing is that, now I'll remind you that we showed that having length, the number of partitions of length less than or equal to n was equal to the number of partitions where the largest part was at most n. This was going from that trick that if a partition has length k, then the conjugate has largest part k. Okay? So I can write this as sum over the lambda such that the first part is less than or equal to n. Lambda such that the first part is less than or equal to n. In other words, all parts are less than or equal to n here. All parts are less than or equal to n minus 1 here. And we computed this. We showed that, if you're only allowed parts that are less than or equal to n, then you can put in as many 1s as you want, as many 2s as you want, up to as many n's as you want. But if you're only allowed parts up to n minus 1, then you get the same thing, but only up to x to the n minus 1. Okay? It's natural to want to put this into a common denominator, so let me multiply top and bottom here by 1 minus x to the n. And then I get what I want, right? Equals x to the n over 1 minus x squared up to 1 minus x. And that's what I wanted because that's this. So that's a proof. Okay. That's a proof. It's a nice, simple proof. This wasn't too hard. Now, what I want to do next is give you a proof without words. So, I mean, this is kind of a computation, but when you practice, you can just see exactly why the answer is this. I mean, here, there's some algebra, which was not combinatorics insight. And I want to just look at this and understand combinatorially why this, which is very clear what I'm doing here, right? I'm just looking at partitions according to these statistics, size and length. Why should that be equal to this? And so let me give you, okay, that was one proof, but now proof 2 is going to be a proof without words, which is like this. If I'm counting this, then I don't know. I'm counting all the partitions that look like this. Okay? And let's say that I want to figure out what the coefficient of t to the n is. So if I want t to the n, that means that the length needs to be n. Which means that the number of parts, which is the number of rows, should be n. Okay? Now, if the number of parts is equal to n, that means, first of all, that I don't have anything below here, but it also means that this row cannot be empty. Right? The last part needs to be there. And that means that I have a column here. I have a first column. Okay? So it has length 1. Okay? So now I'm going to say x is raised to the size of the partition. Now, what's the size of the partition? It's the sum of the parts. In other words, it's the area of this shape. What area does this have? The blue strip. It's a 1 by n rectangle, so the area is x to the n. Okay, so that contributes x to the n. So that's this x to the n. And then what do I have here? What do I have left here? Well, this is a partition into at most n parts. It might have n, but it might have fewer parts. Right? It could be that this thing goes up immediately and there's nothing else in the last row. So this is a partition of n into at most k parts. And if I just tilt my head and I look at it like this, or I guess in some direction, if I think of these as being my columns now, and these as being my rows, then I'm looking at a partition where the parts have length at most n. And what are those given by? We know that those are given by product from I equals 1 to n of 1 over 1 minus x to the n. That's the generating function for this kind of partition, the ones that have at most n parts. And so, given that our partitions have a front row that has weight x to the n, and then the rest is given by this stuff, then you can immediately, immediately, right? I've done this many times before. For you, hopefully you can believe me that, I mean, if it's the first time that you see this, hopefully it seems plausible that this should prove this equality. Because as you run over all the possibilities of partitions, then these are the relevant generating functions. And again, the t to the n comes from the fact that the number of parts is n, and therefore this guy has a weight of t to the n. So this guy has a weight of t to the n. And again, as you practice with this stuff, then you get good at like looking at an identity like this and just know what picture you're supposed to draw that proves the identity. So maybe our next goal will be to question.
At the very beginning, can you explain the one again?
Sure. So maybe I'll run through the whole proof again real quick. So we agree that the left-hand side just counts partitions. According to the x weight is the area of the partition, and the t weight is the height of the partition. And so I'm saying, okay, if I have something of weight t to the n, then it must have length equal to n, meaning that it has exactly n rows. And if it has n rows, that means that this row cannot be empty. So I can at least know that this square is here. This square is part of the partition because I have n rows. And if this guy is in the partition, then because it's a partition, then when you go up, that's also in the partition. Okay? And so then I just look at this strip of the partition, and I just kind of separate the partition into that first strip and the rest. Okay? Now, as I look over all the possibilities, then this part of the partition, when I tilt my head like this, is going to range over all partitions into parts less than or equal to n. And we know that this is the generating function for that. But that only takes care of, okay, so that takes care of the weight of this, but this part also has an area that contributes to this, and so that's why I need to multiply by x to the n so that I contribute the area of this strip as well. Okay? And then I need to multiply by t to the n so that I also consider the t weight, which is the length of the partition. Okay. Let's do another one. And then for the other one, I'm not going to even bother doing an algebraic proof. We're just going to draw the picture. gonna look very similar, but it's not the same. I like this color coding idea. I'm gonna keep doing that. Now, this is going to be equal to the sum, v doesn't fit, sum over n greater than or equal to 0 of, it's going to look a little bit more like the Rogers-Ramanujan one. It's going to have on top a t to the n and an x to the n squared. And in the denominator, it's going to be 1 minus x squared, up to 1 minus x to the n, and 1 minus tx squared, up to 1 minus t x to the n. So you see it's kind of close to the Rogers-Ramanujan, but not quite. If you plug in t equals 1, then you get x to the n squared over the right denominator, but here it appears twice. It's like the square of the right denominator. Okay. So let's prove this. And now I'm just going to give a proof by picture. And I'm going to take advantage of the fact that I already know what the left-hand side does. Right? The left-hand side is the same as this one. So it's counting partitions by the same weight, but somehow it's doing it different. So how is it doing it? What is that n squared about? Okay. We need an idea. Now, you might think, okay, well, here, I kind of did this, and this x to the n was a strip of length n that I took off. That's area n. Right? So here, I want something of area n squared. Okay, so what has area n squared? Square. Which square? Where do we put a square? So I see Kyla pointed in that direction.
I think you want the top corner over.
If I force you to draw a square in here, in some way that's somewhat useful, maybe you will draw a square that starts here and ends where? How big should I make it?
Yeah.
N, but what is n, right? Well, I think this would be weird to do. Maybe, but and it seems to me that the most natural thing is just to put the biggest one that you can. You have to choose something. Well, it seems to me that that's the most natural choice. So let's try to put in the biggest square that we can. So where is that? I guess it looks like, I mean, what you do is you just kind of draw the diagonal until it hits something. Is that a diagonal? More or less? And that's the biggest square that you can draw, right? So. Okay. And it's very natural to say that it has length n. We get to choose what n is because n doesn't mean anything so far. So let's call this length n. Okay? Okay, now let's try to figure out how to count the weight of something like this. Well, first of all, this thing has area n squared, right? And so it does contribute area category, it contributes x to the n squared. How about in the number of parts category? How many parts does this contribute? This thing is forcing me to have at least n parts. So this is forcing me to have at least n parts. Okay, now what do I have here? Here I have a partition. I mean, I do the same trick as I did over there, right? I say if I look at it this way, then this is a partition into parts less than or equal to n. And I already know what that is. This contributes product from I equals 1 to n of 1 over 1 minus x to the I. Okay? Now what about here? Well, here I don't need to tilt my head. This has length n, and so what I have underneath is a partition into parts that are less than or equal to n. And so this is given by product from I equals 1 to n of 1 over 1 minus x to the I. Are we done?
Repeat that last part, please. That bottom part.
This part?
Yeah.
So here what I said is that, what do we have here? We have a partition whose parts are less than or equal to n. Right? And so we know that those are given by this generating function. Now, I would say that we did the x part correctly, but we did not do the t part correctly. Right? Because t should keep track of the number of parts. And we did keep track of the fact that here we added n parts, but we haven't yet taken care of what are the parts that this guy has. This is irrelevant, right? I mean, no matter what happens here, this doesn't contribute any new parts. But here, I do have parts. And how do they manifest in the generating function? Well, it's that every time you choose a part equal to I, you get a new part. I mean, it's the same thing as here, right? This is the generating function for partitions, all partitions, and every time that you have a part equal to I, you're supposed to put a t that tells you I put a part down. This is the same thing, except that I'm now restricted to choose parts of size 1 up to n, because this is the biggest square, and therefore I can't have things that are longer than n here. Okay? And this is the proof. Because then I say, okay, well, you know, the left-hand side counts all partitions. And now let me take all the partitions and split them into groups according to how big what's called the Durfee square is. So this has a name. This is a Durfee square. If the Durfee square has length n, then the generating function for those guys is this times this times this. Which is this.
A question. So, you know how we're using that generating function for the parts being at least n, right?
This one?
The top one. And then when you proved it, I think last class, so you said that was a generating function for the number of partitions of n less than or equal to k. Well, here basically
I switched my letters. So what today I'm calling n. The last time I called k.
Okay, yeah. So in this case, this is like our k right now, right?
So what I'm calling n here used to be the
Okay.
k. So I was taking products from I equals 1 to k because I was only allowed parts that were up to k.
So the question I have is that, does it matter what we're partitioning? Like, will we always just get the same generating function if the parts have to be less than or equal to n, regardless of what we're partitioning?
So the question is so the answer is this, that I'm having a little bit of trouble rephrasing the question, but I think I can tell you a good answer, which is that when I write this down, this is the generating function for every partition of every number. This is the generating function for all partitions in the world. And if you want the partitions that add up to a particular number 100, then you need to pay attention to the coefficient of x to the 100. But here we're listing all of them at the same time. And this is just a funny way of listing them in a different way. And so, here you have some pictures, and it doesn't seem entirely unreasonable that you should be able to do something similar here, right? I mean, this is fine. This we even know what this is. We kind of did it here. And then, I don't know, somehow you need to get this mod 5 from somewhere. I think it's a really interesting question. It's a very hard question, but if somebody wants to write a project about this, I very much encourage you to do it. And you should know that it's a very hard problem that many people have tried to find nice proofs for. And you could kind of study the proofs that are out there. It's a good product. But anyway, these are these kinds of proofs of partition identities by picture. Hopefully this gives you some indication of what you might try to do for problem 6 in the homework, which is give a proof of this identity. And there is a pictorial proof like this. Okay. So the next thing that I want to do is prove this theorem. Another partition identity. And this is known as Euler's pentagonal. Maybe just pentagonal theorem, pentagonal number theorem. And it says the following, that if you take the product over k greater than or equal to 1 of 1 minus x to the k, then you get the following thing. You get the sum over all integers of minus 1 to the n x to the n times 3n minus 1 over 2. And I'll write the first few terms so that you see what this looks like. This is equal to 1 minus x squared plus x to the 5 plus x to the 7 minus x to the 12 minus x to the 15 plus x to the 22 plus x to the 26 minus etc. So it kind of goes plus, minus, minus, plus, plus, minus, minus, plus, plus at these special numbers of this form. Question?
Is that positive and
So it's a little bit strange. It's actually, I did mean to write integers here. Let's see what happens if you put in n equals minus 3. You get minus 3 times minus 10 over 2, which is 15. Which is this one. A little bit of a gimmick, to be honest. But yeah, the positive values of n contributes the first one, and the negative one contributes the second one of each group. Okay. This is a pretty amazing theorem. If you think about multiplying this out, 1 minus x times 1 minus x squared times 1 minus x cubed, etc. If you do it by hand, you'll see that actually there's a lot of terms, and there's a lot of cancellation that happens, and in the end you only get zeros, ones, and minus ones as coefficients. It's pretty magical that you get that, because there's no point in, there's no reason to expect that you would get just ones and minus ones. Okay, so first let's say briefly why is this called pentagonal. Well, maybe you've heard of triangular numbers. You've certainly heard of square numbers. Pentagonal number is the pentagonal version of that, where just draw a pentagon of size 0, then a pentagon of size 1. Okay, so I started with size 0 and I had 1 dot. Then now I have 5 dots. Okay. Now let's introduce another layer. So if I put the one of size length 2, then looks like this. Get points like this. I add 1, 2, 3, 4, 5, 6, 7. So I get 12 points. Then if you put the next layer, you're going to get 22 points and so on. Did I do something wrong?
How do you 12?
I got 12 because I had 5 points, and then I added 1, 2, 3, 4, 5, 6, 7. So it's not how many you add, it's how many you have total after the nth stage. Those are the pentagonal numbers, so that's why this is called the pentagonal number theorem. Okay, let's talk about how you prove this. Well, what would happen if you had a plus here instead of a minus? So we actually already discussed that generating function, 1 plus x squared, 1 plus x cubed, 1 plus x to the 4th. What you do is that the term 1 plus x to the k tells you, do I not choose the number k, or do I choose the number k? And so we said that that was the generating function for partitions into different parts, where each part k, you either don't choose it or you choose it. So, on the left-hand side, how do I say this? The coefficient of x to the n in the left-hand side is, if it was plus, then I would just be summing over lambda, a partition of n, into distinct parts. Actually, it would just be, I would be summing 1, because, if it was 1 plus x to the k, then I would be, every time I have a partition to distinct parts, I would get 1 new contribution. So the total would be just the number of partitions of n with distinct parts. But I have these minuses, right? And what those minuses do is that when when I have something like, imagine that I put 1 minus x squared, 1 minus x cubed, 1 minus x to the 4th, etc. And I'm supposed to take a term out of here. So let's say that I chose this term, and then this term, and then this term, and then this term, and then I choose ones from there on. Okay? So what do I get in the end? Well, I get x to the 1 plus 3 plus 4. And that's my partition into different parts. The partition of 8. And what sign do I get? Well, I get a minus sign every time that I chose a part. So it's going to be the number of parts. And so here what I'm going to get is the sum like this. Okay? And the point is that this is usually 0. So for most numbers, the number of partitions into an even number of distinct parts is equal to the number of partitions into an odd number of distinct parts. Those numbers are usually equal, and if they're not equal, then they're off by 1 or minus 1. So we need to show. So to try to show that this number is usually 0, what we could try to do is just find a bijection between the even and the odd partitions here. So let's say that S is the set of partitions of n into distinct parts. And I can write this as S even union S odd, where I mean even number of parts or odd number of parts. And again, the point is that these two sets have roughly the same size. They're usually equal to 0, but then for those weird values of n, they're off by 1. Okay? And so what I can do is try to find a bijection between these two sets. Okay? And so what I'm going to do is the following thing. Okay, so let me consider for any partition like this, I'm going to make two definitions. So I'm going to let the number of boxes that I have here, I'm going to call this E of lambda. Okay, that's the size of the smallest part of the partition. And then I'm going to go down this diagonal until I can't anymore. I'm going to go down the first diagonal and see how many parts there are there. I'm going to call that D of lambda. Okay? Where this is lambda. And now I'm going to define a function from S to S, which is going to be my attempt at a bijection. Now I know that this bijection shouldn't always work. It needs to fail sometimes, but it should usually work. Okay? It's kind of a weird goal to try to come up with something that usually works but sometimes doesn't. But that's what we need to do. And the way that I'm going to do it is this. Two cases depending on which one of these is bigger. So I'm going to say, if D of lambda is less than E of lambda, then I'm going to let F of this guy, so I have, I don't know, maybe 5 things here, and then I have 3 things here. How can I turn this into a partition that changes the parity of the number of parts? Because the idea is that F should take even things to odd things and odd things to even things. And when I say odd and even, I'm referring to the number of parts. Or in other words, the number of rows. What I'm going to do is I'm going to take more or less the same shape. Okay. And I'm I'm going to take these three guys that were here and I'm going to put them down here. So I get this, and I lose this. In other words, maybe what I'm going to do is, so I lose this stuff, and just to remember that we lost it, I'll put little empty red dots here. Okay, so I took these three guys and I took them out and I put them underneath here. Okay. So we agree, right, that if this had an even number of parts, this has an odd number of parts and vice versa. That's what I do if the diagonal is shorter than the last thing. What do I do in the other case? Well, I'm actually just going to do exactly the opposite thing. So if I have only two dots here, and I have three here, then I'm going to take that shape and okay, so then again let's so we take out those two guys, so they were here, and now they're not here, and let's put them here and here. Okay. These are the red dots, they're still here. So that's what I do. Okay? So what property does f have? Well, f has the property that f of x is equal to x. Because if you're in this situation, right? So let's say that you start with this guy. So you apply f, which means that you take these three guys and you put them down here. Okay? So now, what happens when I apply f to this guy? Well, you see, here, this guy has length 3, and if this diagonal had length 3, then the next diagonal has length at least 3. Right? Which means that we're in this case. The diagonal is greater than or equal to the bottom, and therefore, what f does is exactly reverse what you just did. And similarly for the other case, if you start with this one, you'll see that you end up in this case. Okay. So this is a bijection between even and odd. Yeah?
What if when you remove in the top part, now you could keep going. Like so you took
In this case,
yeah, you took those off when you mapped it,
I
right?
took these three off and I put them down here.
Yeah, but then what if now the new one, the dy increases because it can go down more?
If this new diagonal is even longer,
Yeah.
it's still the same thing because it's still the diagonal is going to be bigger than so I'm saying that the new diagonal is either bigger than 3 or at least equal to 3. And in either case, it puts me in this case. So, okay, so that, notice that f of x, or f of lambda is lambda, and lambda and f of lambda have opposite parity. So, why is this not a proof that this is always equal to 0? It looks to me like we just paired up the evens and the odd ones.
Sometimes if they get the red one to run into the blue ones.
So there's two places and only two places where this can go wrong. And that's if the blue and the red interact with each other. So if let's say that this guy has 1, 2, 3, 4, and let's say that the red goes 1, 2, 3, 4. So what does F do in this case? So the red and the blue have one point in common. We're in this case, so the diagonal is greater than or equal to this, and so what I'm supposed to do is take the diagonal and bring it down. And it used to be that you could do that, but I'm taking off one of the points here.
Opposite.
Wait,
Am I doing the opposite? Oh yeah, sorry. So, because the diagonal is bigger than this, I'm supposed to take these 4 guys and put them over here. But the problem is that I cannot do that because I took the last point away. So I can't place it right there. Okay? So this is one case where the function is not defined. And this is when this is n, and this is this is n, and then this is n minus 1. Okay? In which case, what's the area here? The area is, I have n squared, okay, plus n minus 1 plus n minus 2 plus 2 plus 1. Which is n squared plus n times n minus 1 over 2, which is n times 3n minus 1 over 2. Okay? Which is great, right? Because that means that this, in this case, this bijection shouldn't have worked, and the reason it doesn't work is that there's this one weird guy that ruins it. And what sign does that guy have? It has sign minus 1 to the n, which is this sign. Which is perfect. So that this is one of the exceptions. And the other exception is very similar, but it occurs, I guess, when, what happens when,
F maps X to X.
it's when this is n plus 1 and this is n. Or let me say, this is n. This is a bad picture, I'm sorry. But here I wrote the numbers n and n minus 1. And the other case where this goes wrong is when the numbers here are n and n. And then you can see that in that case also the bijection does the wrong thing, and it produces the case when n is a negative integer. It gives that contribution. So it's an almost bijection, but except it misses these weird cases. And so these are the ones that survive our bijection. And that's why Euler's pentagonal number theorem works. Which actually, there better be exceptions because this can't be equal to 0. You can't multiply this and get 0. Right? But it's pretty amazing that this is the very small number of exceptions. So you get this. Yeah?
Is that how you proved it, or did he use something completely different?
I'm not sure how he proved it, but this is the favorite proof now, I think. At least it's my favorite. I think it's very nice. Yep.
Sorry, on that second one, is that diagonal, the entire length is n, or is that?
No, so it's kind of like I did here. So this is if there's n blue dots and n red dots.
Right.
And this is if there's n blue dots and n plus 1 red dots.
So doesn't that work if you take away n from the bottom, then you have n rows still?
Or maybe I mean the opposite? So in this case, I'm in case B, right? And I have an exception in case A. Yeah, I think it's the opposite. So I think it's n. It's hard to think live in front of you guys. There's another exception, and it's a small tweak of that. Think about it, and then you'll by finding the exception, you'll by thinking about what it should be, you'll find it. let me just tell you two things to conclude this discussion. So here's one. Notice that what is this? This is the sum over all partitions, right? And now what is this one? I get this. So let's multiply them. Here I get 1, and here, what's the coefficient of x to the n? Well, to get an x to the n, I can do p of n times 1, or I can do x to the n minus 1 times x. So I get minus p of n minus 1, or x to the n minus 2 times this, minus p to the n minus 2, or x to the n minus 5 times this, plus p to the n minus 5, etc. So what did we just prove? We proved that p of n satisfies this very weird recurrence. Very strange. And actually, this is how Euler computed these partition numbers. He wanted to know how many partitions there are of 100. Well, he just kind of made this table, and you can really do it by hand at this point with some patience. And really, if you want to compute the whole list of partition numbers from 1 up to n, this is the recursive way to do it, and this is the best way to do it. If you want to find one particular p of n, then there are better methods that are much more sophisticated. But I think I'm not mistaken in saying that this is really what Euler was after. He wanted to compute these numbers, and so he discovered this whole stuff to compute them like this. The other aside that I wanted to talk to you about is this one. So what if I do the same thing, but instead of using k, I now use the Fibonacci numbers? So you do 1 minus x, 1 minus x squared, 1 minus x cubed, 1 minus x to the 5th.
Only one minus x.
It's a good point. I guess this one appears twice. Okay, well that might seem very strange. You end up getting partitions into Fibonacci numbers and split into even and odd parts. You could multiply this out, and you'll see that there's a lot of cancellation. And again, this has only coefficients equal to minus 1, 0, or 1. For rather different reasons. Or at least I'm not aware of any proof like the one that I described. So there's a theorem. When I was in grad school, Richard Stanley asked me this question, and so I proved it. So I have a little paper where I proved this theorem. And it turns out actually that there was an earlier paper, and oddly enough, it's by somebody else in this department. So this is actually Neville Robbins who first proved this result. And then in my paper, I actually give a recursive way of computing these numbers. And then there's actually 2 follow-up papers where this is studied in more detail. But this is kind of a question that you can just ask. You know, if you just put some sequence here, then you end up counting partitions. Like in this case, you're counting partitions of n into Fibonacci numbers, according to whether there's an odd or an even number of some n's. And you can use different sequences here, and it's, I think, an interesting project to figure out what sequences can you put here so that you still have this kind of balance property between even and odd. And I think that's a pretty wide open question at this point that one of you might like to investigate. Okay, I think that's a good place to stop.